All right, were there any questions? No. Let's take a look at the lab here. So at 3A, we're adding ammonia and ammonium. This is actually a buffered solution here. It's buffered with a little bit of ammonium so that the pH doesn't go too high. If the pH goes too high, we get too much hydroxide, and then we end up precipitating out magnesium, nickel, and zinc, which we don't want to. We want to leave those in solution. So now in that case here, if you don't get that much precipitate here, though, we'll just have to add a little bit more ammonia to bump up the pH. You want enough precipitate to analyze for iron, chromium, and aluminum. And if you barely have any precipitate at this point, then try to get some more. Even though we're trying to prevent precipitation of these, if we just don't have enough precipitate here, we're not going to get very good results. Well, anyway, from here, we're, again, dissolving the aluminum in excess hydroxide to form the tetrahydroxoaluminate ion. And we're oxidizing the chromium-3 from chromium-3 to chromium-6 using hydrogen peroxide. Then we have to heat to remove the hydrogen peroxide. You can just heat it on the hot plate, maybe in an evaporating dish. You just want to just drive off the hydrogen peroxide. It's going to be driven off as oxygen. Hydrogen peroxide normally decomposes, so just look for bubbles. Once the bubbles of oxygen stop, it's pretty much done. But you might not see much, so just keep heating it. Okay, then we, at this point though, we could add lots of hydroxide. Now here we got to be a little bit careful. Here we can just go ahead and dump in a lot. But if you add in a lot of excess hydroxide, then you have to neutralize it with HCl. So that means you're going to have to add more HCl than you typically would, but that's okay. We add the HCl to neutralize the sodium hydroxide, and then the HCl to dissolve our precipitate here at iron 3, and then precipitate it out with the hexacyanoferrate 2 to make this. This is Prussian blue. This should be a blue precipitate. The solution is also going to be blue, and so it's not a blue solution that we're looking for, it's a blue precipitate. So you should centrifuge it and make sure there's a precipitate at the bottom of that. Okay, then for the aluminum, we dissolve it and then reprecipitate it. Here we can add plenty of excess ammonia. Plenty of excess ammonia is not going to do anything. We just want to maximize the amount of precipitate we get here. And then wash the precipitate as usual, and then dissolve the precipitate, and then add aluminum. Aluminum's, the dye, it's going to be in one of the dropper bottles in the hood, and will form a red lake. This is also a precipitate. A red solution is not a positive. It's got to be a red precipitate, and it's going to be a gelatinous precipitate sitting at the bottom of the test tube. That's the red lake. Okay, so here at this point, we should be in with chromate. Remember, chromate in acidic solution, dichromate in basic solution. And so this, got it backwards. Chromate in basic solution, dichromate in acidic solution. So this should be yellow chromate. We can precipitate out. This is going to be a yellow precipitate. Again, not a yellow solution. The solution will be yellow. You just got to add the barium here and make sure we get a pale yellow precipitate sitting at the bottom. Yeah. All right, now we should be able to make it to the calcium flame test. If we can make it to the calcium flame test, then we only want to clean the platinum once for this round. That is, we don't want to have to clean this wire once for the sodium test and then clean it again for the calcium test. We just like to clean it once because it's a bit of a pain to clean. And so how do you clean the platinum wire? So once you have to, one, you'll have to check it out from the stockroom. Okay, 2, you'll get a test tube and fill it with some concentrated HCl. The amount of concentrated HCl that you want is enough to cover the wire, but not enough to cover the glass. You don't want the glass on this to hit the liquid. The reason is as you're heating this, the glass is going to get very hot. And then if you dip this into liquid, you might quench the glass, which will cause it to fracture and break. And so I would just cover the platinum wire, maybe 2/3, with hydrochloric acid. And so this is the technique that we're going to use to clean the platinum wire. You're going to dip it in concentrated hydrochloric acid. Now be careful. You don't want to spill concentrated hydrochloric acid on your finger. So what I always do is I put it in a beaker like this, and leave it on the counter. That way, if some drops of hydrochloric acid spill off this, it's not going onto my hand. If I'm holding this, the drops will go onto my fingers. And so you dip it and then burn it off. Dip it and then burn it off. What we're looking for is we're looking for the flame to be totally colorless. And the wire should not impart any color to the flame. And then you know it's clean. We're going to clean this inside the hood because we don't know what contaminants are on here. You know, it could be poisonous, so we don't want to inhale the vapors of it. And so clean this in the hood. Working with burners in the hood is a bit more of a pain. You have to get a larger flame because the wind is constantly blowing through there and it's trying to blow out the flame. Okay, once you have it clean, then we're going to do the calcium test first. The calcium is not so easy to detect. The reason is because it gives kind of a faint red color. This is called a brick red color. And so the color is not so intense, and it doesn't live for very long. The color lives for about a second, and then it's gone. And so it burns off quite quickly. And so if this were contaminated with calcium, it's so easy. Just burn it off, a couple of seconds, it's gone. But the situation here is this. You know, if this were contaminated with sodium, then it'd take a long time to burn off. In fact, if you did the sodium test first, you would have trace quantities of sodium, which gives a bright yellow-orange flame. And you'd never be able to see the calcium. And so always do the calcium first. Once you detect the presence of calcium, then try the sodium. If you're unsure what calcium, the flame looks like, we have calcium nitrate in the hoods, in the dropper bottle. So you can get a couple of drops of calcium nitrate, put it on there, and see what color calcium should burn. Hopefully nobody contaminated those. Because what's common is somebody contaminates that with some sodium, and then you get a bright orange, and you can't even see the calcium. It's totally drowned out. But there should be no sodium here, assuming everything worked out okay. We should just have calcium. Okay, is that clear for the flame test? About cleaning this and doing... Okay, once you test, you're going to test positive for calcium. So once you test positive for calcium, then get a drop or two of your original unknown solution, put a drop or two on the wire, and then test for sodium. You're going to test positive for sodium, you're going to need bright orange yellow flame. Do that inside the hood because original unknown contains species that you don't want to inhale, like chromium, silver, etc. Okay, then let's continue here. So we precipitate out the calcium and then tested after dissolving it back. Solution. Then to the remaining ions, we're just going to add sodium hydroxide. We don't care if the pH gets too high or if there's too much hydroxide in this case. In fact, we want lots of hydroxide. In fact, if we don't add enough hydroxide, what we end up with is white magnesium hydroxide, green nickel hydroxide, and white zinc hydroxide. We have to add excess hydroxide to this, otherwise this doesn't work. If you add just the right amount of hydroxide, we end up with 3 precipitates here. We need to add excess hydroxide so that one of the precipitates, zinc hydroxide, which is white, forms tetrahydroxo zincate ion, zincate 2. And so the excess hydroxide is to make sure that the zinc is dissolved into the complex. Okay, once we have the zinc dissolved in the complex, we're going to add the hexacyanoferrate 2 ion and some hydrochloric acid to destroy the complex, and we get this gray blue precipitate here. That would be a positive test for zinc. Now to the 2 remaining precipitates, which would be the white magnesium hydroxide and the green nickel hydroxide, nickel 2 hydroxide, we're going to add ammonia. And here we're going to add excess ammonia because what's going to happen is the nickel is going to form an amine complex, whereas the magnesium does not form an amine complex. Now, how do you know? Well, we just looked this up in the table, basically. This is hard to predict from what we know. So it just so happens that nickel, it's the same thing here. Why didn't the nickel form a hydroxyl complex and the magnesium form a hydroxyl? So they don't. That's why. It's just from observations, factual observations. So in this case, the nickel will dissolve, however the magnesium won't, with excess ammonia. And so you try to crush it up, make sure you dissolve all the green precipitate. There should be no evidence of green precipitate over here. Once all the green precipitates dissolve, then we're going to wash and clean our magnesium hydroxide precipitate, dissolve it, add some magnesium reagent, which is a dye in a dropper bottle, and then reprecipitate it out with sodium hydroxide. Here we're going to get a blue lake, similar to the red lake, which is going to be a gelatinous blue precipitate instead of a gelatinous red precipitate. And then with the nickel, we're going to add some DMG, dimethylglycine, which is going to precipitate out the red PBT, which is the nickel, DMG2. All right, so those are the major cations. Here, we're going to continue the discussion of the rest of the tests next time. But are there any questions here up to this point? No? All right. We haven't had a quiz.